Hello everybody. This video is in response to a question from one of my other videos by Arpit Singh, who is asking whether or not the groups U17 and U25 are cyclic groups. And so it's probably good if we start off by saying, well, what are these groups? So remember that U of n, or sometimes also written U sub n, this is equal to the units, right? The group of units in Z mod NZ. Okay, so you're looking at the integers modulo some positive integer n, and then you're looking at the unit group. Sometimes this is also written as Z mod NZ times. We're looking for invertible elements. And these are precisely the elements, right, which are going to be relatively prime to n. Okay, so as an example, if we were going to look at, say, u of, I don't know, how about 8, then we're going to be looking at the classes, right? And I'll use square brackets here around the numbers so that we know that these are really the classes, but normally we wouldn't write the square brackets. So this is going to be the number 1, or the class of 1, not the class of 2, because 2 is not relatively prime to 8, but then we would get the class of 3, not 4, we'll get the class of 5, not 6, and we'll get the class of 7, and then we're done because we're looking at mod 8 here. So, right, 0 through 7 gives us a transversal. So U of 8 would be this 4-element set, and actually one can show this is a group, right, under multiplication. So as a group under mod n multiplication. All right, so here we have a group of order 4, and well, as soon as you have a nice group, you can ask, is it cyclic? So what does it mean to be cyclic? That means it has a generator, right? So there'd be one element, and if you take all the powers of that element, you would get the entire group. It's certainly not going to be the 1, all right? All the powers of 1 are 1. What if we took 3? And actually, right, just this is, again, an abuse of notation. So abuse of notation, we're just going to write this as 1, 3, 5, 7, knowing all the time we're treating these as representatives of equivalence classes. So let's look at 3. If I take 3 to the first power, I get 3, right? Of course, this is mod 8. 3 squared is 9, but that's congruent to 1. Okay, as soon as I get a 1, I'm done, right? Because now the next one would be a 3, and then a 1, a 3, and a 1. So the order of 3 is actually 2, not 4, right? I can only generate the numbers 1 and 3. So the group generated by 3 here will actually just be 1 and 3. What about 5? Well, 5 to the first, of course, that's just 5. 5 squared is 25, but 25 mod 8 is also 1. So the group generated by 5 is just 1 and 5. All right, well, that doesn't work. How about 7? Well, obviously 7 is congruent to 7. How about 7 squared? Well, 7 squared is 49, but modulo 8, that's also 1. So, right, and we already knew that the group generated by 1 is just 1. So in fact, none of the elements generates the entirety of U8. So U of 8 is not cyclic. All right, so it's a reasonable question then for any particular n to ask, is it cyclic? Here, 8, the answer is no. What if the answer is not 8? Right? Well, there's a general answer to this question, which may be more than you want, right, when you're first learning group theory, but generally, we can actually say U of n is cyclic if and only if n is of the form, well, let's see. It could be 2, or it could be a power of an odd prime. So here p is an odd prime. Or you could double one of these. So it could be 4, which is 2 times 2, or something of the form 2 times p to the a. And that's it. If it's not of this form, then u of n is not cyclic. And if it is of this form, then u of n is cyclic. Okay, so at the higher levels, you probably just want to use this result. But maybe this is your first course in abstract algebra or second course in abstract algebra, and they actually want you to show that u of n is cyclic in a particular case, like 17 or 25. So let's do this manually. So if we're looking at u of 17, and I want to know, is this cyclic? Well, actually, there's another highfalutin way we could do this. So remember, this is z mod 17 z, and you're going to take the unit group. Now, because 17 is prime, z mod 17z is a field. All right, so this forms a field since 17 is prime. And there's a nice classical result which says that the unit group of any finite field, okay, and this is certainly a finite field, there's not an infinite number of elements, is cyclic. So that would immediately tell us that U17 has to be cyclic. Again, maybe you don't have that result in your introductory group theory course, so let's do it manually. So what are we looking at here in terms of the elements? Well, there are things that are going to be relatively prime to 17, and well, man, that's just going to be almost everything, right? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and we want to try to find a generator in here. Well, it's not going to be 1, right? If you take the powers of 1, you just get 1 out. All right, let's try 2. So, in fact, what I'm going to do here, I'm going to have here just start writing powers down. And then this is going to be 2, so this is going to be like some k. And this will be 2 to the k, right? And of course, we're talking mod 17. So 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. But let me make an observation that 16 is congruent to -1. And as soon as I get to -1, I'm in my happy place, because I know if I square -1, I'm going to get 1. So I can jump all the way down here to 8. And that means I'm going to square here 2 to the 4th, right? 2 to the 8th, I know that's going to be a 1. Which tells me automatically 2 is not going to do the job. This does not generate. It's only going to give me 8 of the elements, right? And in fact, if I wanted to, I can fill these in, right? 2 times -1, that's just going to be -2, which is the same as 15. 2 times -2 is -4. -4 is going to be the same as 13. All right, 2 times -4 is -8. -8 is going to be the same as 9. All right, so that's it. All right, 2 is not going to be the generator. But this also tells me I don't have to worry about 2, 4, 8, 16, 15, 13, 9, and well, I knew I didn't have to worry about 1 already. All right, so none of those are going to be generators either. Okay, let me go to the next thing on my list. Let's look at 3. So 3 to the 1st. 3 to the 1st is equal to 3. 3 squared is 9. 3 cubed is 27. But 27 mod 17 is congruent to 10. Okay, 3 times 10 is 30. But 30 mod 17 is 13. All right, 3 times 13 is 39. But mod 17, that's 5. 3 times 5 is 15. All right. Oh, hey, 15 is -2. That'll make life easier. 3 times -2 is -6. Okay, -6 is the same as 11. All right, how about 3 times 11? Well, that's 33, which is -1. I found that magic -1, and it happens in the 8th position, which means I'm not going to get the 1 until the 16th position. So that's going to be my generator. It's going to be a 3. Okay, and maybe you don't believe me, right? We can prove it's going to work, or we could also just fill this in. Whoops, 14, 15, right? We can look at all the powers, right? Okay, 3 times -1 is -3. Okay, mind you, right? This is the same as 16. -3, that's the same thing as 14. 3 times -3 is -9. That's the same thing as 8. Let's see, 3 times 8 is 24, which is the same thing as 7. 3 times 7 is 21, which is the same as 4. 3 times 4 is 12, same as -5. 3 times -5 is -15, which is the same as 2. 3 times 2 is 6. And 3 times 6 is 18, which is congruent to 1. And you can check, right, manually, right? We've gotten every single element, right, in U17. All right, so this means that U17 is generated by 3. Now, this doesn't mean that 3 is the only generator, right? In fact, there's going to be more. But we have found a generator, and that's all we need to do to prove that U17 is cyclic. All right, how about U25? Well, I could write down all of the elements, how many they're going to be. Well, we're going to get all the numbers from 1 through 24, and then we have to toss out any that are not relatively prime to 25. Well, let's see. 5 isn't, 10 isn't, 15 isn't, 20 isn't. Okay, so there's 24 numbers minus 4. So that's just good to know. The order of U25 is going to be 20. So we have to be able to generate 20 numbers. All right, well, once again, we can just start taking possible generators, right? We're not going to start with 1. How about 2? So 2 to the k, and here we go. 1, 2, 3, etc. So 2 to the 1 is 2. 2 squared is 4. 2 to the 4th is 8. 2 times 8 is 16. 2 times 16 is 32, but 32 is the same as 7 mod 25. Okay, 2 times 7 is 14. 2 times 14 is 28, but 28 is the same thing as 3 mod 25. All right, 2 times 3 is 6. 2 times 6 is 12. And 2 times 12 is 24, but 24 is the magic -1. And so this tells me I can keep going, and all I have to do is double this. And when I get to 20, I'm going to get my 1. Ah, this is wonderful. I just found it with our first try, a generator. All right, U of 25 is going to be generated by the class of 2. All right. So that's just the easy way to do it. So a few things that I'm doing in here that oftentimes students don't remember to do. As I go through and take powers of 2, you'll notice I'm not going to keep computing higher and higher powers of 2. Like, so if I didn't do 64 when I got to the 6, right? I didn't do 2 to the 6 equals 64. I just took the class of 32, which was the same as the class of 7, multiplied 7 by 2. Right? Here I multiplied 14 by 2, not 64 by 2 to get the next one. And if you keep reducing as you go, that will make your computations a lot easier. Now, I am all the time using, right, that as soon as I get to -1, then I know for sure that I'm not going to get a 1 any sooner. All right? So maybe we should prove that as a little lemma. Right, so if, let's say n is some integer greater than 1, so we're going to be working modulo n. Okay, and if a is an integer such that a to the k is congruent modulo n to -1, where k is some positive integer. All right, I'm not worried about it equaling 0. Then a to the 2k, and this is not actually the interesting part, a to the 2k is going to be congruent to 1 modulo n. And that's obvious, because if you square a to the k, you get a to the 2k. And if you square -1, you get 1. So that's not the interesting part. The interesting part is, okay, furthermore, if k is minimal, such that a to the k is congruent to -1, then 2 times k is minimal, such that a to the 2k is congruent to 1. Okay, so again, the first part of the proof, all right, so the first part is easy. If I take a to the k and I square it, this will be congruent to -1 squared, but a to the k squared is just equal to a to the 2k, and -1 squared is equal to 1. All right, so what about the second part? That's the interesting part. So in this case, let me just write down sort of generically what's happening when I go from a to the first, a squared, etc. So I start with a to the first, a squared, a cubed, and I keep going, and then at some point I get a to the k minus 2 and a to the k minus 1, and then all of a sudden at a to the k, I find I'm congruent to -1. Okay, that's my assumption. And what's important here is none of these terms before are allowed to be 1, because if one of them was 1, then I would have just started repeating again, right? Anytime one of these, you get a 1 in here, you're just going to start cycling over and over again. So if I had a 1 before, well, the -1 should have occurred before as well, right? Because it's part of the cycle. Okay, so we know that none of these, none are congruent to 1. And for that matter, none of them before a to the k are congruent to -1. Now, what happens after a to the k? Well, the next one is going to be a to the k plus 1, but that's just a to the k times a. And a to the k is congruent to -1, so this is congruent to -a to the 1. Keep going, a to the k plus 2. Well, that's just congruent to -a to the 2, because again, the a to the k is just -1, right? I could think about this as a to the k times a squared, and this is congruent to -1. Okay, I keep going. All right, next one will be a to the k plus 3, which is congruent to -a cubed. ... Now let's look at the second to last one. I get a to the k minus 1, and that's going to be just congruent to, well, each time I have a negative, and this is, oh, I'm sorry, I said 2k minus 1. This should be 2k minus 1, right? So it's really, let me write it like this, k plus k minus 1. Okay, so I have k plus 1, k plus 2, k plus 3, ... k plus k minus 1. This is 2k minus 1. All right, and so this should be -a to the k minus 1. And then finally, the last one, that'll be a to the 2k. And a to the 2k, that's going to be congruent to, really, a to the 2k is the same as a to the k plus k. And we know that'll be -a to the k. Okay, but a to the k is -1, so this is just congruent to 1. Okay? So the first time we get the 1 is actually in this 2k position, because what about all these other ones before it? We know the first bit here, none of those could be 1 or -1, right? How about all of these? Can they be congruent to 1 or -1? Well, no, because they're just the negatives of the terms we got in the first half of this sequence. So none of these are congruent. None are congruent to 1 or minus 1. All right. So the first time you get the negative one, if that's at k, then the first time you can get a positive one is at 2k. All right, and there we go. So that's how we can always determine, right, if our unit groups are cyclic. We can obviously there's a nice big theorem, right, which is what you want to use in general. If these numbers n get really huge, you really don't want to be looking around for generators, right? In fact, this is a very challenging open problem, finding generators for large n. But if the numbers are reasonable, it's really just as simple as writing down a bunch of powers, right, of numbers in here and trying to find, I mean, really all you really need to find is -1, because then you can just double the length and you'll get, you'll figure out where the positive one is going to occur. And you just want one that generates everything, right? So you just need to figure out how many elements are in your unit group, and then you're good to go. All right, well, Arpit, I hope this is what you were looking for. I hope this is very, very helpful. Have a wonderful day, everybody. Take care. Bye-bye now.